In this lecture, I'll show how to use logarithms to solve what are called inverse exponential problems. These are problems in which you have an exponential equation and you're looking to find the value of a variable that appears in the exponent. This is a review of the, let me get my pencil here. This is a little review of the equations that we use when we solve these inverse problems. First, remember the notation. Log to the base 10 is abbreviated as log. Log to the base e is abbreviated as ln. Any log of 1 is 0. Here we're going to see, taking the log to the base 10 of 1 gives me 0, log to the base e of 1 gives me 0. We take the log of a number that's equal to your base, the answer is 1. That's because this is really a 10, log to the base 10. That didn't come out. Okay. Log to the base 10 of 10. These numbers are the same. The answer is 1, and that's what we're seeing right here. Again, for this expression, ln is log to the base e, and when the argument is e, these two numbers are the same. The answer is 1. The rule concerning exponents is that the exponents go out in front. So if I have a log to any base b, I don't care what this base is, the x goes out in front and multiplies log. It also multiplies any number that's sitting out there. If I have 6, log to the base 10 to the 3, the 3 goes out in front and multiplies the 6, giving me 18 log of 10, but I know that log to the base 10 of 10 is 1, so the whole answer here is 18. That's an example. And that's an example of these convenient ones. If I have log to the base 10 and has an exponent associated with it, remember that exponent goes out in front. Then I'm left with, in this case, 19t times the log of 10. The log of 10 is 1, so the whole answer is 19t. Same when you're taking the natural log of an exponent to the base e. Whatever is in the exponent comes out in front. In this case, it's t divided by 10. That comes out in front, right here. Multiplies natural log of e, but natural log of e is 1, so the whole answer is t over 10. Sometimes this convenience with these ones doesn't happen, but you can still do the problem. I have log to the base 2 of 25t divided by 3. The entire 25t divided by 3 comes out in front. Here's 25t divided by 3. Multiplying log of 2. In this case, you can't just dismiss log of 2 as 1 as we could in these other occasions. Instead, you would have to find the value on your calculator or remember it. In this case, you would have 25t over 3, and the log of 2 is 0.3010. Everything here is multiplied together. Here's the first inverse problem, and it's fairly common. It concerns continuously compounded interest, and the formula for continuously compounded interest is A, the amount in your bank account equals P, the principal, that's the amount you deposited, or the principal of the loan, the initial value of the loan, times E, Euler's number, raised to the RT. Remember, R is your annual percentage rate in decimal, and T is the time in years. If you're using R as annual percentage rate, then T is time in years. If you're using R as the daily percentage rate, then T is in days. The units of these are tagged together. Now the question for the inverse problem is, say I want to triple my money. I want to triple my initial deposit. I have some kind of an account or some kind of loan that pays me 5% annual percentage rate. How long do I have to keep my money in this account in order to triple my money? Now sometimes students go, well, wait a minute, I don't know what you put in there, so I don't know how long it would take you to triple your money. But if you can do it like this. The initial value is P. If I triple it, that's a P, B. If I triple it, I want 3 times it, right? So no matter how much I put in, I want 3 times the money back out. So here's how I substitute these values into my original equation. The amount I want is 3 times my principal, 3 times whatever I deposit. Here's the deposit amount, which is just P because I don't have a value for it. E raised to the 0.5t. The reason it's 0.05 is because annual percentage rate is 5%, so rate is the decimal equivalent, which would be 0.05. Now I can eliminate the principal here, this unspecified principal, by dividing both sides by p, and I get 3 equals e raised to the 0.05t. This is an inverse problem because I'm trying to find the value of a variable that is up here in an exponent. I can't find this value until I get it down to the main part of the equation, get it out of being an exponent, and then I can just solve it in the usual manner, isolate the variable. To get that exponent down, I use logarithms. So I'm going to take the log of both sides. That's important, both sides. So I take the natural log of 3 on this side, and I'll take the natural log of e raised to the 0.05t on this side. I chose natural log because it makes things more convenient, but I don't have to, and I'll show that in a minute. Alright, so natural log of 3 is just a calculator button. That's just what that is. Okay. The 0.5t is up here. This whole exponent comes down and multiplies the natural log of e. I know that the natural log of e is 1. So the next line here is natural log 3 equals 0.05t. Now I just isolate t by dividing both sides by 0.05. T equals natural log of 3 divided by 0.05. On the calculator I can work that out. 4771 divided by 0.05, and I would find that I would have to keep the money in the bank for 21.97 years, about 22 years, in order to triple my money at 5% interest. You aren't required to use natural log because you have the e. You can use log and you will get the same answer, and I'm going to demonstrate that now. Here I have the same problem, but instead of using natural log, I'm going to use log. So I take the log of both sides. Right. The same exponential rule applies, and this exponent, 0.5t, comes out in front and multiplies the log that I have left, log of e. Now that doesn't immediately reduce to 1, but I can still continue the problem. All I have to do now is isolate the t. So I have is a log of 3. Remember, that's just a number. You could even put that in parentheses if you want. 0.05t times natural log of e. To isolate the t, I divide by the 0.5 times the natural log of e. This is multiplication. Same on the other side. And of course, all I'm left with by design is just t on this side, time. So that's what I have on this line. T is a log of 3 here, divided by 0.05 times the natural log of e. The natural log of e you can find on your calculator. You can either hit the log button, and then you can try to hit the e to the 1 button like that, or you can just approximate it by the log of 2.71828, and you'll get the value 0.43429. That's what's right here. When I divide that out, I get the same answer as I did before, 21.97 years. So if you take, if you use either logarithm and you do it consistently, you will get the same answer. Here's the allowance problem. There was supposed to be an L in there. My generous and wealthy family triples, T-R-I-P-L-E-S, triples my allowance every week. The first week I was given just a measly penny, but things would probably work out well very soon. Assuming that I don't save any money from week to week, I would like to know, when can I buy, we like manual transmissions, and we want a Lexus convertible. Maybe you don't want a manual with a Lexus. I'm not sure. I know if you want a Porsche, you always want a manual transmission, although I heard of someone who thought they wanted an automatic with a Porsche. At any rate, I want this Lexus convertible, but I also want to be able to have the manual transmission. The cost is something about $40,000. So I want to know, when am I going to get $40,000? Which week am I going to get $40,000 so I can buy this Lexus? Here is the equation. This is how that equation is written. the amount that I get equals the original amount times, and it's going to be tripled. So the base is 3, and it's tripled every week, 3 to the t. You have to know how to write this for the test. So I've written it right here. This is the equation. So the way to do these kind of equations is first write down the general formula. Then go through and substitute the values that are given, the values that you know from the problem. Well, I know that I want this amount of money, $39,815. I know that originally I was only given a penny, right, for my first week of allowance. So we want everything in dollars, so that's 0.01 times, and then of course 3 to the t. This is an inverse problem because I'm solving for the variable that is in an exponent. I use logarithms to bring that exponent down. The first thing I'm going to do is divide both sides by 0.01 and get about 3 million on this side, or almost 4 million on this side, equals 3 to the t. This is more convenient, although you don't have to do this. You instead could use the multiplication rule for logarithms. But now that I have this problem, I'm going to take the log of both sides. I could take log, I could take ln, and I would get the same answer. But here I've taken ln. So I take the natural log of this almost $4 million equals the natural log of 3 to the t. T is up in the exponent, the t comes down as a multiplier. And then I isolate t by dividing both sides by the natural log of 3 and find that it's almost 14 weeks, maybe more than I can bear, to wait to buy this Lexus. Okay, do you see how to do the problem? If you don't, you can always contact me. Here is a good email. uaacalculus@yahoo.com, or you can call my office. And I will walk you through the problem again. Here's an exponential problem concerning epidemics, and I'm going to do it two ways because I want to show you that not everything is an inverse problem. So let's say I have running the 500 cows, but I have 2 sick cows, and I know how the disease is spread. Perhaps I should have used A0 there when I wrote this equation. The number of sick cows is the number of initially sick cows, E, and then it's this expression has to be determined by people who track diseases, people who work for the CDC and other places that watch how different diseases are spread. Not all of them are spread quickly. Some, of course, are slowly. Some, for example, plague. Plague is fairly slow when it's spread from animals to people. However, once it gets to where it can be transmitted from people to people, then it can go faster. So this has to do with the disease and how it's spread. But let's say you're just given that. I think in the homework problem I used P as the initial variable for 4 sick cows. And I'm not sure what the equation was for that. But here, it doesn't matter. All right. The idea is that you have, whatever you have here is the initial number of cows that are sick, or people that are sick. Here are the number that are sick at some time t, and this is determined and given to you as how this disease spreads. So my question is, I want to go on vacation for 2 weeks, and then I want to return and deal with this. Do I dare go anywhere? I've got 2 cows. Am I going to lose the whole herd when I come back? Is it all going to be gone? So this is not an inverse problem. Instead, it's an evaluation problem. The way to find that out is that you take your initial expression and you substitute the values you know. Well, I know that initially I have 2 sick cows, so I put the 2 here. And I know I want to be gone for 2 weeks. I'm assuming the 0.03 is in weeks and t is in weeks. All right, or per week. So I would put, I know this value right here, and I know that's 2. So actually I would get 2 sick cows, and I'm going for 2 weeks. You see, there's no variable to solve that's in an exponent. This is just an evaluation. And when I evaluate it, I find that I come back and 3.5 cows will be sick. So I'd say, well, that's okay. decide if that's all right. This one doesn't spread very fast. Now let's look at an inverse problem concerning epidemics. This is a problem that's given in the homework. How long before all my cows are sick? So here's what I had for my original expression. Right? This is the number that are sick at time t. This is the number that are initially sick, and here's the time. I know that this is 2, so I can put a 2 here. I want to know the time, so I put the t here. I don't know the value of time, and I want to know when the whole herd is sick. That means when 500 cows are sick. So here's what I get with that substitution. And now I want to solve for a variable that's in the exponent. I can't solve for it when it's up in the exponent. I have to bring it down. To do that, I use logarithms. And here again, I'm using ln. You could just as well have used log. That was pretty bad English. All right, you could have used log. Here I used ln. Doesn't matter what you do, you get the same result. Unless you do this. This is something you can't do. I can't take log of this side and then take ln of this side. No matter how much you would like to do that, you can't do that. You have to take the same logarithm of both sides. So using ln of 250 equals ln of 0.3t. Here's my exponent. That comes out in front as a multiplier. Important to remember that it multiplies when it comes out in front. Now, this is very convenient because the ln of e is 1. So all I have to do is divide by the 0.3, and I find that in 18.4 weeks, the whole herd is gone. It seems like if in 2 weeks, that 2-week vacation, not very many cows got sick, and now suddenly here I am only 18 weeks later and the whole herd is gone. That's because this is an exponential equation. If you remember the graphs for exponential equations, they might start off a little bit like this, and then they really take off. So while you didn't show much change here in 2 weeks, by 18 weeks you're way up here and you've lost your whole herd.